This is Module 1, Lecture 2-2 on conducting research. In the first portion of this lecture, we talked about the skills of reasoning. In this portion, the second portion of this lecture, we will discuss hypotheses and research in general. Excuse me while I set my pointer. Well, it's one of these. Okay. Thank you for being patient. We had discussed in the previous lecture this theoretical framework in the context of experimental design. So there are several facts, fact 1 and fact 2, that are shown here with hypotheses or gaps that are separating them. There can be strongly supported hypotheses or weakly supported hypotheses. True gaps. The true gap, as we stated, was the typical approach, the expected approach of rigorous scientists in the forefront of science to come up with new hypotheses, develop rationale and experimental design to test those hypotheses, or that hypothesis in this case. If supported, then it goes back in as a supported hypothesis, strongly or weakly, depending upon the nature of the experiment. Weakly supported hypotheses, if new approaches come up and they're challenged and not supported, they can be bumped out and a new hypothesis has to be established. So let's talk about this idea of hypothesis. The source for this discussion is Carl G. Hempel, Philosophy of Natural Science by Princeton Hall, Incorporated, New Jersey. The 4 stages of an ideal scientific inquiry are the observation and recording of all facts, analysis and classification of these facts, induction, derivation, and generalizations from them, and further testing on the generalizations. So this is basically the scientific method, although we word it a bit differently, and we'll continue through the semester to develop that, going from abstract, less recognizable by us to the more recognizable and direct statements that we typically hear. The first 2 of these stages are specifically assumed not to make use of any guesses or hypotheses as to how the observed facts might be interconnected. This restriction seems to have been imposed in the belief that such preconceived ideas would produce bias and would jeopardize the scientific objectivity of investigation. So what you will hear in the scientific community in the process of seeking funding and promoting your own research career as a professional research scientist is that hypothesis-driven research is preferable to a wild goose chase or a fishing trip. And that, in essence, is what is being stated in these 2 slides. We are not merely empirical observers. We are now expected as scientists in many of the disciplines to be driven by hypotheses. So an hypothesis is untenable. It's a collection of all facts. That approach is untenable, especially in nearly all disciplines today, because the collection of all facts would have to await the end of the world, even if all the facts up to now cannot be collected. You simply can't review every single relevant or related and pertinent, even remotely important research article that's published. You don't know everything that's going on in research laboratories and so on and so forth. So the first phase should then be that all the relevant facts should be collected. So an extensive effort to do so, relevant to a specific problem. In other words, we hear the request to make a statement of the problem, such as in a thesis or dissertation. For what particular sorts of data it is reasonable to collect is not determined by the problem under study, but a tentative answer to it that the investigator entertains in the form of conjecture or hypothesis. I just love how philosophers write. Anyway, empirical facts or findings can be qualified as logically relevant or irrelevant only in reference to a given hypothesis, but not in reference to a given problem. Therefore, the hypothesis is between the facts or the findings from empirical science and the theoretical framework, if you want to put it into the picture, the illustration that we had used. So a finding is relative to a hypothesis H if either its occurrence or its non-occurrence can be inferred from H. So in other words, a finding that can be determined through well-controlled experimentation must be within an experimental design that tests the hypothesis. Otherwise, the data produced has nothing to do with the hypothesis. Data can be called positively or favorably relevant to the hypothesis, or negatively or unfavorably relevant to the hypothesis. In other words, your results either support your hypothesis or they do not support your hypothesis, and typically we do not often hear, at least, the phraseology used such as my data prove my hypothesis. We either support it or we don't. It can be strong support or weak support, and of course our spectrum of associations from 0% to 100%, the causality, are very important in that context. And it all comes down to experimental design and overall approach to investigating or studying the problem. So tentative hypotheses are needed to give direction to a scientific investigation. Such hypotheses determine, among other things, what data should be collected at a given point in a scientific investigation. So it generates a framework to contain our thoughts and ideas, and experiments, and experimental approaches. In other words, more so today than probably ever before in history, research is hypothesis-driven. And the philosophers seem to back that up. Thus, if a particular way of analyzing and classifying empirical findings is to lead to an explanation of the phenomena concerned, then it must be based on hypotheses about how these phenomena are connected. Without such hypotheses, analysis and classification are blind. So we all know this through our training and studies in science. As I said, I just love the way the philosophers state things. So induction in scientific inquiry. Induction is sometimes conceived as a method that leads by means of mechanically applicable rules from observed facts to corresponding general principles. So basically from specific to general. Induction rules would therefore have to provide a mechanical routine for constructing, on the basis of the given data, a hypothesis or theory stated in terms of some quite novel concepts which are nowhere used in the description of the data themselves. So in other words, setting up an hypothesis requires the presentation of assumptions and premises that logically lead to the hypothesis as being the only possible outcome of the analyses. There are no generally applicable rules of induction by which hypotheses or theories can be mechanically derived or inferred from empirical data. Typically, as we will see, you are in the literature and familiar with the content area of what's known and what isn't known, and what needs to be done to know what isn't known, and you ask a question or a series of questions, and the answer to the question or questions is your hypothesis. So the transition from data to theory requires creative imagination, and if we just reflect back on our illustration, that of course is obvious. In other words, proof equals reasoning plus evidence. So our formula sticks in here too. If we make a claim we're trying to prove, we have to have creative imagination in our reasoning to accompany the evidence that we collected, either from the literature, both from the literature and from the experiments that were carefully controlled and designed. Scientific hypotheses and theories are not derived from observed facts, but invented in order to account for them. So this is an important aspect of the intellect and creativity of the scientist above and beyond the technical capabilities of the individual. So our technical capabilities bring us the observed facts, well-controlled and designed experiments, and then intellect and creativity go beyond that. So all you have in science are your ideas. Give away all your ideas before you can document that they're yours, and what are you left with? So they constitute guesses at the connections that might obtain between the phenomena under study at uniformities and patterns that underlie their occurrence. I think one should be in here, that one might obtain between the phenomena under study at uniformities and patterns that might underlie their occurrence. So what is the nature of the association? So this requires great ingenuity, especially if they involve radical departure from the current modes of scientific thinking. The authors of our textbook discuss this and warn against radical departure from current modes of scientific thinking. Either crash and burn or win a Nobel Prize, I think, is the phrase that they used. So the inventive effort required in scientific research will benefit from a thorough familiarity with the current knowledge in the field. So you have to know the content, you have to know how people do things, because they will be the individuals reviewing your work, your proposed work, and your completed work for funding and publication, respectively. So scientific objectivity is safeguarded by the principle that while hypotheses and theories may be freely invented and proposed in science, they can be accepted into the body of the scientific knowledge only if they pass critical scrutiny, which includes in particular the checking of suitable test implications by careful observation and experiment. Again, this seems all to be circling around the nature of the experimental design, the rationale for the approach to achieve the specific aim for a particular hypothesis, and the objectives overall. So we will see there's an intrinsic cohesion or cohesiveness in an experimental proposal and research report. Scientific knowledge is not arrived at by applying some inductive inference procedure to antecedently collect data, but rather by what is called the method of hypothesis, by inventing hypotheses as tentative answers to a problem under study and then subjecting them to empirical test. Again, this is reinforcing the philosophical correctness, if you will, of hypothesis-driven research, not merely a fishing expedition to see what you find and then try to make sense of it. Again, our approach from the theoretical framework to identifying gaps, being creative in our idea of asking questions, assessing the problem, asking the essential questions, answering those questions, and in essence generating hypothesis or hypotheses, and then having the technical capability of testing that hypothesis or those hypotheses in such a way that the empirical data collected truly can be determined as to whether it supports or does not support the hypothesis, to reinforce the hypothetical ideas within the theoretical framework. Then let's transition to this question: what is research? First, of course, we make the statement what research is not. It's not mere information gathering. It's not a fishing expedition. It's not a wild goose chase. It is hypothesis-driven. There's a structured approach. The scientific method is what we teach in biology departments in the BIO1 laboratory. And we expect ourselves to understand and appreciate and be able to quote the scientific method throughout our career as scientists or individuals with an expertise in science. Research is not mere transportation of facts from one location to another, not merely rummaging for information, and it is not a catchword used to get attention. What research is originates with a question or problem. So the way I describe it is if you identify the problem, assess it appropriately, and creatively, you can generate one or more questions, answer those questions, and you are very close to, if not having, your hypothesis in hand. It requires a clear articulation, which I can't even pronounce, clear articulation of a goal, follows a specific plan of procedure, usually divides the principal problem into more manageable sub-problems. So what we're seeing is we are asked to provide a goal and objectives, and it will have an implicit experimental design approach and an explicit one once that part of the proposal or the research is achieved, and we'll have specific aims for achieving the objectives that contribute to the achievement of the goal. Is guided by the specific research problem, question, or hypothesis, so hypothesis-driven. It accepts certain critical assumptions, requires collection and interpretation of data in attempting to resolve the problem that initiated the research. By its nature, it is cyclical, or more exactly, helical. So research methodology in summary. The methodology controls the study. So well-designed and controlled experiments is a statement, a phrase that I use frequently. It dictates the acquisition of the data. So by what means will you acquire the data? Arranges them in logical relationships. So there must be a consistent and cohesive flow of ideas, information, statements, predictions, and so on and so forth. Methodology and all of that throughout a research experiment or project. It sets up a means of refining the raw data, so how will you work with the data once you collect the raw data, and contrives an approach so that the meanings that lie below the surface of those data become manifest. So what is the rationale for the experiment, such that when the data is collected, there's an obvious theoretical framework, even a practical methodological framework within which the data can fit and obviously make contributions either at the technical or at the theoretical level. Finally, it issues a conclusion or series of conclusions that lead to an expansion of knowledge. So what is the extension of the work? In some cases extrapolation, but definitely fit back into the theory. The research methodology has two primary functions: to control and dictate the acquisition of the data, to corral the data after acquisition and extract meaningfulness from them. So we're still kind of in that abstract description mode, and we will proceed through our future lectures and getting more and more specific. So this is the Figure 1.1, the research cycle from one of our textbooks, presenting the research process as cyclical. So here in number 1, I have to enlarge my screen a bit so I can read it a little bit better for you. Thank you for waiting patiently. Okay, sorry about that. Research begins with a problem, an unanswered question in the mind of the researcher. 2, the research sees the goal in a clear statement of the problem. 3, the research subdivides the problem into appropriate subproblems or specific aims and objectives. Each subproblem seeks guidance through a specific research question or appropriate hypothesis. We'll try to discuss the idea of a working hypothesis or global hypothesis, which I envision as that theoretical framework sometimes, but depending upon the nature of the study, you can either have one hypothesis or several hypotheses under a blanket hypothesis, the working hypothesis, and so on and so forth. It really depends upon the discipline you're working in and the individual you're training under or the group that you're working with. So the research holds the hypothesis or question until all the data are in and interpreted. At that point, the hypothesis is supported or rejected, the question adequately answered or not, and of course, we feed into that from number 4 as well. The research posits tentative solutions to the problems, a problem or problems, through appropriate hypotheses. These hypotheses direct the researcher to the data, and feeding in here at this subpoint, and that takes it all the way around to 6, excuse me. And 5 is encountered along the way. The research looks for data directed by the hypothesis and guided by the problem. The data are collected and organized, and everything converges here on number 6. Research interprets the meaning of the data, which leads to a resolution of the problem, thus confirming or rejecting the hypothesis or hypotheses, and for providing an answer to the question that began in the research cycle. And we go back to our theoretical model and look for gaps and evaluate hypotheses, and we're off and going again. This ends the lecture for Module 1, Lecture 2, Part 2.